Last time we took a look at a method for finding volumes that involved setting up the problem as a Riemann integral, using the definition of the Riemann integral as a basis for the method. Our first applications of the method involved finding the volume of a cylinder, finding the volume of a cone, and finding the volume of a hemisphere, all of which we could check using formulas from geometry. We saw that the results we got from the Riemann integral method matched up with the results that we expected from our geometry formulas. So that gives us some confidence that the method is sound. So what we're going to be up to this time is taking a look at some unfamiliar situations where we have to use our integral method to get a solution. This time there won't be a way to check our answers. We won't be able to rely on an alternate formula to find the volume or later in the presentation arc length in question. We have to just rely on our method to give us the results. The two applications we're going to look at today are what we're going to call volumes of revolution, and then also arc length, which is another way of saying the length of a curve. As a reminder, this is the outline for our basic Riemann integral method for solving problems. We split the problem into pieces that we know. This would be similar to using rectangles to approximate the area under a curve. Next, we find the contribution of each piece. In the case of area under a curve, that's finding the area of the rectangle. In the case of the volume examples we did last time, that was figuring out the volume of a disk. Once we know how to find the contribution of each piece, then we get an approximate solution to the entire problem by adding up all the pieces. In the case of area under a curve, that's adding the areas of rectangles together. In the case of the volume examples from last time, that means adding up the volumes of all of the disks. Finally, we note that as we take more and more pieces, we get better and better approximations to our solution. And that suggests that we can get an exact solution by taking the limit as the number of pieces goes to infinity. Once we have that limit, then we need to recognize that what we have done is set up a Riemann integral, and then we use the fundamental theorem of calculus, or sometimes a computer, to finish off the problem and get a numerical answer. Some of the geometry that we used last time will come in handy again today, so there are a few facts that we'll remind ourselves of. First off, for a right triangle, you need to remember the Pythagorean theorem. That should be a right angle there. So that a squared plus b squared is equal to c squared. And then our similar triangles, that's when we have the larger sides, I can call A, B, and capital C. And then inside that larger triangle is a similar smaller triangle. And the idea is that the ratios of the sides is always the same. Finally, we have the volume of a disk, which we can view as a short cylinder. Here's our radius r, and the thickness we often call delta H. Sometimes h, depending on the situation. When that's the case, then the volume is the area of the circle, pi r squared, times the thickness, delta H. We're going to apply our basic method now to an unfamiliar situation, what we're going to call volumes of revolution. A volume of revolution is where we take some function and revolve it around the x-axis. At least initially it'll just be the x-axis. So if this is my curve f of x and I spun that around the x-axis, it would trace out kind of a bell-shaped shape. That bell shape we would call the solid of revolution, and the volume of that shape we would call a volume of revolution. Now, I want to point out before we move on that if we sliced the figure perpendicular to the x-axis, then the resulting slices would once again be disks, where the radius is just the value of the function. This GeoGebra applet allows us to visualize a volume of revolution. On the left-hand side, we get the graph of the function. Here we're graphing f of x equals square root x, and we are looking between a is 2.4 and b is equal to 7. On the right-hand side, we see the shape we would get if we revolved that function between the two limits around the x-axis. And we can kind of play with the a and the b to see what happens if we take a bigger region. Same goes for a. We could move that to the left or right. And we can also change the function. Instead of square root x, I could use a function like sine x plus 0.5x, and we see on the left we get a more interesting function maybe than the square root x was, and on the right we see the resulting kind of bell shape that we would get if we revolve that curve around the x-axis. This applet will be posted on Moodle, so you're free to experiment with different functions to see what kind of shapes you can generate. As a final note, it does also compute the volume of that solid of revolution for you down in the bottom corner. To find a volume of revolution, we'll rely on our method from last time. We split the problem into pieces that we know that approximate the situation. As we've pointed out, we're going to be able to use disks again. We'll need to figure out how to find the volume of each disk. Then we add up all of the volumes of all the disks to get an approximate total volume. And then we get an exact volume by taking a limit as we let the number of disks or slices go to infinity. Finally, we recognize the solution as an integral, evaluate it using the fundamental theorem, or sometimes a computer. Our first example involves finding the volume of the shape we would get if we revolve the function x squared around the x-axis from x equals 0 to x equals 4. We start by sketching a rough picture of what this shape would look like once we have performed the revolution around the x-axis. We begin with f of x equals x squared. The drawing won't be to scale, but it won't really matter either for our purposes. So we imagine kind of pulling the curve out of the screen towards us as we revolve or think of revolving it around the x-axis. And what we end up with is kind of a funnel-like shape that we've sketched here. Recalling our method is to slice the figure into pieces we know. Here, if we slice perpendicular to the x-axis, then we get shapes that would resemble thin disks. The radius of one of those disks we'll call r sub I, and the thickness we'll call delta x sub I, since we are slicing along the x-axis. Step 1, we need to figure out what the volume of one of our slices or one of our disks would be. We already know that in general that's going to be pi times the radius squared times the thickness, delta xi. Now we have a little bit of work to do because we can't leave the r sub I as a variable in our volume. We need to get that in terms of x. The way we do so is to notice that whatever that radius is, it's the distance from the x-axis up to the curve x squared. In other words, it's just f of xi, where xi marks the location of that disk, which means we would end up with xi squared as the radius for the ith disk. Now the xi isn't something we've drawn in the picture, but it would represent the x value for the location of that disk. After some algebra, we see the volume of the ith disk would be pi xi to the fourth times delta xi. Next, we get an approximation to the volume of our solid by adding up the contributions of all of the disks. So we'd get a sum from 1 to n if we had n disks, and we'd be adding up these pi xi to the fourth times delta xi's. Now, following our usual method, if we get an approximation to our volume by adding up n disks, and we would get a better approximation by taking more disks, then we get an exact value by taking a limit as n goes to infinity, where n represents the number of disks, and we're adding up the contributions of each. Once we've written down that limit, then we need to recognize that what we've really done is write down a Riemann integral. And rather than use that definition to calculate the integral, we want to use the fundamental theorem of calculus. So we recognize that what we've done is create an integral that goes from 0 out to 4 for the function pi x to the fourth, where the delta xi becomes the dx. This is something that we know how to integrate. We can do this one by hand. We could also check it with something like Wolfram Alpha. But the idea is we can pull out the pi because it's just a constant, and then the antiderivative of x to the fourth would be x to the fifth over 5. And we go from 0 to 4. So we get pi times 4 to the fifth over 5 minus 0. Which gives a final result of pi times 1024 all over 5. And that should conclude our first example. Our second example of finding a volume of revolution involves revolving a function around an axis that's different than the x-axis. So here we're going to revolve the function e to the x, but we're going to revolve it around the horizontal line y is equal to -1. And we'll do so between x equals 1 and x equals 2. So we get a quick sketch of what this figure is going to look like. Here's our axis of rotation, y is equal to -1. And so we have to imagine revolving our curve now around this axis. We see that the resulting shape is something like a tree stump or a Christmas tree stand or something like that. Now when we go to find the volume, the idea is the same as before. We want to slice this into disks that we know. We slice perpendicular to the axis of rotation, and that gives us thin disks, and we'll have to figure out how to get the volume of each one of those. Note that the radius of the ith disk now goes from y equals -1 up to the curve, not from the x-axis up to the curve. Step 1 is to find the volume of one of those disks, and we do know that whatever the radius is, the volume of the disk will be pi times that radius squared times the thickness, delta xi. And now our job is to figure out how to write r sub I in terms of x sub I, which again would be the location of the disk along the x-axis. So we're going to think of r sub I in two pieces. We have the part that goes from the x-axis up to the curve, which is f of xi, plus the part that goes from the axis of rotation up to the x-axis, which is the value 1. That makes our r sub I f of xi plus 1. Because the function is e to the x, the final expression for our radius will be e to the xi plus 1, and that gives a volume for our disk of pi times e to the xi plus 1 quantity squared, all times delta xi. Now ordinarily our second step would be to add up the contributions of all of our disks. So we'd have the sum I equals 1 to n and so on. Then our third step would be to take a limit as n goes to infinity of that sum. We can save a little bit of writing, and hopefully this will be okay. We're going to go straight to the resulting integral. So the volume of our solid will go from 1 to 2, x equals 1 to x equals 2, and we're integrating pi times e to the x plus 1 all squared, and the delta xi would become the dx again. The integral that we end up needing to evaluate is one that we can do by hand, so we can use the fundamental theorem of calculus to get the value for the integral, but we will have to do a little bit of algebra first. If I expand e to the x plus 1 all squared, I would get e to the x times e to the x, which is e to the 2x. I would get 2 times e to the x, and finally I would get a 1. Now each of those pieces is one that we can handle individually. So we still have the pi, and now an antiderivative for e to the 2x. Keeping in mind the chain rule would be at work, we have e to the 2x over 2. And then the antiderivative for 2e to the x, leave the constant alone. The antiderivative for e to the x is just itself. And finally the antiderivative for 1 is x. We evaluate all of this between 1 and 2. And all that's left is a little bit of computation. So plug in x equals 2, we get e to the 4th over 2 plus 2e squared plus 2. And from that we subtract what we would get if we plugged in x equals 1. So that's e squared over 2 plus 2 times e plus 1. We can simplify this a little bit. Get e to the 4th over 2. 2 minus a half would be 3 halves e squared. And that should conclude the example. Next we switch gears, and instead of taking a look at finding volumes, we see if we can use our integral method to find lengths of curves. Before we tackle the much harder problem of finding lengths of curves, let's remember how we find lengths of straight lines. This comes from the distance formula. If we have 2 points in the plane, x1, y1, and x2, y2, then the distance between them is given by the square root x2 minus x1 squared plus y2 minus y1 squared. This is actually the Pythagorean theorem, which is illustrated in the graphic. The vertical distance here is the difference in the two y coordinates, y2 minus y1, and the horizontal distance here is the difference in the two x coordinates, x2 minus x1, and those form the legs of a right triangle. That means we know the distance between the 2 points, given by d, can be found using the Pythagorean theorem. So that would be the square root, the sum of the squares of the sides, and that's exactly what the distance formula tells us. To find the length of a curve, we'll use our knowledge of how to find straight line lengths in the process. Number one, we're going to split the problem into pieces we know, pieces that approximate the situation. Here, we're going to take a curve and approximate it by straight line segments. After that, we have to figure out the contribution of each piece. In this situation, it'll be to find the length of each segment. Then the length of the curve will be approximately the sum of the lengths of the segments. Finally, we'll get an exact length for the curve if we take the limit as the number of segments goes to infinity. We then recognize that what we've done is set up a Riemann integral. Typically in an arc length problem, the integral we end up with is a very difficult integral to do by hand. So for arc length, we will often use a computer or a site like Wolfram Alpha. This GeoGebra applet shows us the process of taking a curve and splitting it up into line segments. The function here is sine x, but we could change that if we wanted to. And we've split the curve up into 3 line segments, which you can see does not do a great job of approximating the actual curve. To do a better job, we would have to increase the number of line segments. That's done with the slider for n here at the top. For n equals 5 segments, we are looking a little better. You can see that at 15 segments, already we have a pretty good approximation to the curve. Now, we can keep going. If I slide all the way over to the maximum number of segments of 100, then we really see virtually no difference between the curve itself and the approximating segments. That means if we had a way to figure out the length of each of those 100 segments and we added those lengths together, we would get a really good idea of how long the sine curve is. What we're going to do next is actually derive a formula for arc length that we can then apply to any curve that we want. It's worth at least going over the main steps for the derivation, because the formula, if you just look at it from scratch, is certainly not an obvious formula. So I think it's worth spending a little bit of time seeing where the formula comes from. To get us started, I want to take a look at what one of our line segments would look like. How would we find the length of just one of those segments for our function f of x? So let's pretend this is our function, and let's say this is my ith line segment. So I'm going to go from here to maybe here. So that's xi minus 1 to xi. So this could be the first segment, could be the second, the third, the 100th, the 1000th. It's just the ith segment. Now, we already know from the distance formula that the distance between these 2 points would be the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates. And now we have to remember that the y-coordinate for a point on a curve is just the function value. If we add up all of those lengths, then we get an approximation to our arc length, or the length of the curve. Next up, we do some perhaps odd-looking algebra, where inside the square root, I'm going to multiply and divide by the same quantity. We sometimes call this multiplying by a clever form of 1. Note that xi minus 1 is the same as delta xi, and that appears twice. So that what I'm doing is dividing by delta xi squared, but at the same time, so I don't change the value of the expression, I'm multiplying by delta xi squared. You can check that nothing's changed by multiplying through by the delta xi squared. We would get cancellation with the denominators and would be right back to where we started. Now we have to recognize that underneath the square root, the first term is just 1 because it's delta xi squared over delta xi squared. And in the second term, I'm going to bring everything inside the square. So instead of the numerator squared over the denominator squared, I have the fraction squared. The delta xi, notice, has been taken outside of the square root. So the square root of delta xi squared is just a plain delta xi. I'm also taking the limit as the number of segments goes to infinity, so we have gone from an approximate arc length here to an exact arc length here. From here we jump straight to the arc length formula. So let's see what just happened. The delta xi, as it does in all of our Riemann integral examples, becomes the dx. A harder leap to make is the fact that inside the square we have an equivalent definition for the derivative of f. The idea is that as n goes to infinity, xi minus 1 approaches xi, and so we have this difference quotient in the limit becoming f prime of x. Our next example shows what is a fairly straightforward application of the arc length formula, where we're going to find the length of the curve, f of x equals sine x, between 0 and pi. We start with a quick sketch of what the sine curve looks like. Now the general arc length formula we know is given by the integral from some point A to B of the square root 1 plus the derivative of our function squared. In this particular case, since our function is sine x, the derivative of our function is cosine x. Thus, applying the formula, we now have the integral from 0 to pi of the square root 1 plus cosine x squared. Like many arc length problems, the integral we end up having to do, because it involves a square root, is difficult to do by hand. So we often turn to some sort of computation device, either a handheld calculator or the website Wolfram Alpha, to carry out the actual numerical calculation for us. One way to get Wolfram Alpha to do so is to type integral and then the function we're integrating, square root of 1 plus cosine squared from 0 to pi. We get about 3.82 from Wolfram Alpha. We can do this in a second way because Wolfram Alpha actually understands what arc length is. So instead of the integral we end up with, we just say find the arc length for sine x between 0 and pi. And we should see that we end up with the same numerical approximation, and then we get a picture as well for what the arc length represents. So our final result is about 3.82. So we just finish up our example here by noting the numerical value that Wolfram Alpha gave us. We know that the length of the curve is roughly 3.82 between x equals 0 and x equals pi. And that concludes our example.